Pick one star out of the sky tonight and look at it for a moment. The light arriving in your eye left that star before anyone you have ever met was born, and it has been traveling every second since. Everyone knows the next part of this sentence. Light does not experience time. For the photon, the journey was instantaneous, born and absorbed in the same moment, no aging at all. But here is what that telling leaves out. It quietly puts somebody on the beam. It imagines a passenger with a wristwatch and reports what the watch says. And relativity does not tell you the watch reads 0. It tells you there is no wrist. Meanwhile, the light itself has been counting the entire way, 500 trillion times a second, keeping a tally so exact we can read it back to a fraction of a single cycle, with not 1 second recorded anywhere in it. So what does it actually mean to say that light has no age? By the end of tonight, you will know exactly. Settle in, hit subscribe if you're new here. Because by the end of this, the word timeless will never mean the same thing again. Now, let's slowly ease into this. Part 1. The photon that noticed nothing. There is something in the room with you right now that is almost as old as the universe, and it has no age at all. Both of those statements are true, and the distance between them is where we are going to spend tonight. Let us start at the beginning, because this story has an unusually clean one. Picture the universe when it was very young, only a few 100,000 years past its own beginning, and still far too hot to be anything you would recognize as space. The first few minutes had been a furnace, and even after that furnace subsided, the whole cosmos sat at temperatures above 100 million degrees. For thousands of years it stayed like that, a uniform glowing soup of bare nuclei and free electrons, a plasma with no structure and no landmarks, filling everything. Light existed inside that soup, but it did not go anywhere. A photon would be born, and almost immediately slam into a free electron, be absorbed, be re-emitted, and slam into another. The universe was not dark. The universe was opaque, which is a very different thing. It was bright in every direction, and you could not see through it for even the shortest distance, the way you cannot see through the inside of a cloud. Then, when the universe was about 380,000 years old, it had cooled to roughly 3,000 Kelvin, and something changed that has never changed back. At that temperature, for the first time, a lone electron drifting past a lone proton could be captured and held, instead of being immediately knocked free again. Electrons and protons began to bind together into neutral hydrogen atoms all across the cosmos, in a wave that swept through everything in a geological blink. Astronomers call it recombination, which is a slightly odd name for something that had never happened before. And as each electron settled into place beside its proton, a small amount of energy was released, because a bound electron carries less energy than a free one, and the difference had to go somewhere. The difference went out as light, a packet of energy, released at the moment an atom came into being, moving away at the only speed it could possibly move at. A photon. Our photon was not the first. Photons had been made and unmade by the trillion for every second of the universe's existence up to that point. What made this one different was that the universe had just, in the same instant, become transparent. With the free electrons swept up into atoms, there was almost nothing left to scatter off. And so, for the first time since the beginning, light could simply go, in a straight line, for as long as it liked. Our photon went. It headed first into what cosmologists call the Dark Ages, and the name is accurate. There were no stars yet. There were no galaxies. There was hydrogen and helium, spread almost perfectly evenly, with the faintest ripples of density running through it, ripples that gravity had already begun to pull on. Over 100 million years or so, those ripples deepened into the first concentrations of matter in the history of everything, the seeds from which all structure would eventually grow. It was slow, and it was silent, and it was the most consequential thing that had happened since recombination. The photon passed straight through it, and it noticed nothing. Then the first stars lit. They were unlike anything burning today, made of nothing but hydrogen and helium, with no heavier elements to help them shed heat, which meant they could grow to enormous mass before they stabilized. Some may have been hundreds of times the mass of the Sun. They burned ferociously and briefly, a few million years each, and died in explosions that scattered the first oxygen, the first carbon, the first iron, into a universe that had never contained any. Between them, the first supermassive black holes were assembling, with a speed we still cannot fully explain. The photon crossed through all of it, and it noticed nothing. Galaxies came next. Matter that had been drifting for hundreds of millions of years began to gather into rotating structures, and the sky filled with the fires of uncountable young stars, fusing hydrogen into helium, and helium into carbon, and carbon into everything that would eventually make a planet, an ocean, a body. Millions of years turned into billions. Galaxies collided and merged. Superclusters assembled. In one unremarkable spiral, in one unremarkable arm, a cloud of gas, enriched by earlier generations of dead stars, collapsed under its own weight and lit a small yellow star. And around that star, a disk of debris clumped into worlds. On the third of those worlds, water pooled, and something in the water began to copy itself. The photon flew through the outskirts of that galaxy on its way in, and it noticed nothing. After nearly 14 billion years, the photon crossed the last few thousand light-years of its journey and struck a small piece of metal orbiting the third planet, part of a detector built by creatures who had been capable of building anything at all for a few thousand years. Its energy was absorbed. An electron in that metal was lifted into a higher state. A number changed in a memory register somewhere, and the photon, at the end of a journey that had begun before there were atoms, before there were stars, before there was anything at all to see, ceased to exist. Here is the part that has been repeated in classrooms and documentaries for a century. To the photon, none of that happened. Not the Dark Ages, not the first stars, not the assembly of the galaxies, not the 14 billion years. The standard telling says that from the photon's own point of view, the moment it was emitted and the moment it was absorbed were the same moment. It was born and it died in the same instant. The universe aged around it, and it did not age at all. That telling is repeated everywhere, and there is something true buried inside it, and it is also, in a specific and important way, wrong. Not wrong in a nitpicking, technical, ask-a-pedant way. Wrong in a way that makes the truth stranger, and, once you see it, considerably harder to unsee. Because the version everyone has heard quietly assumes that there is somebody on the beam. It assumes a passenger, a small traveller riding the crest with a watch on its wrist, and it tells you what the watch reads. And the physics that gave us this whole picture, the physics of Einstein and Minkowski, and the century of measurement that followed, does not merely say the watch reads 0. It says there is no wrist. Part 2. The sentence everyone repeats. The sentence goes something like this. Light travels at the speed of light, and at the speed of light time stops, so a photon experiences no time at all. Its journey, however long, is instantaneous from its own point of view. Light does not age. You have heard it. Possibly you have said it. It appears in science documentaries, in undergraduate lecture halls, in popular books written by people who understand relativity perfectly well, and in 100,000 internet comments underneath videos about black holes. It is one of the most successfully transmitted ideas in all of popular physics, and the reason it travels so well is that it is short, it is dramatic, and it is very nearly true. I want to take it seriously before taking it apart, because the sentence is not the product of sloppiness. It is the product of a real and correct chain of reasoning, and the chain only breaks at the very last link. Here is the chain. Moving clocks run slow. That is not a philosophical claim. It is a measured fact, and we will spend a whole part of tonight on how thoroughly it has been measured. The faster something moves relative to you, the slower its clock ticks relative to yours. The relationship is not linear. At ordinary speeds, the effect is so small, it is undetectable without atomic clocks. At half the speed of light, a moving clock runs at about 87% of the rate of yours. At 90%, about 44%. At 99%, about 14%. At 99.99% of the speed of light, a moving clock ticks roughly once for every 70 ticks of yours. The pattern is unmistakable, and it points somewhere obvious. Keep adding nines, and the rate keeps falling. Take the last step, arrive at the speed of light itself, and the rate reaches zero. The clock stops. Therefore, for light, no time passes. Every step of that argument is fine, except the last one, and the last one is not a small mistake. It is the difference between a very large number and infinity, which is to say, it is the difference between a hard problem and an impossible one. But before we pull on that thread, it is worth knowing where this whole picture came from, because the person who first got tangled in it is the same person who eventually untangled it, and he was 16 years old at the time. In 1895, Albert Einstein was a student at the Cantonal School in Aarau, in northern Switzerland. He had left the German school system, and by his own later account, he spent a good deal of that year daydreaming about a specific problem. He had learned Maxwell's equations, the great unification of electromagnetic wave, that had shown light to be an electromagnetic wave, and he asked himself a question that any curious 16-year-old might ask, which is what makes it such a good question. He asked what he would see if he ran alongside a beam of light at exactly the beam's own speed. Think about what that would mean for an ordinary wave. If you run alongside an ocean swell at the swell's own speed, the swell stops moving relative to you. It becomes a frozen hill of water, stationary, going nowhere. So by the same logic, if you run alongside a light wave at the speed of light, you should see a frozen electromagnetic wave. The peaks and troughs would still be there, spread out in space, but they would not be going anywhere, and they would not be changing. A standing, motionless ripple in the electric and magnetic fields. And here is what the boy in Aarau realized, and what bothered him for the next 10 years. There is no such thing. Maxwell's equations do not have a solution that looks like that. An electromagnetic wave exists because a changing electric field generates a magnetic field, and a changing magnetic field generates an electric field, each one continually regenerating the other, and that mutual regeneration is what carries the wave forward. Freeze it, and the regeneration stops. Freeze it, and you no longer have a wave. You have a static configuration of fields that nothing in the equations permits, and no arrangement of charges could produce. He had imagined something that the laws of physics as he understood them flatly could not describe. Einstein wrote about this much later, in the autobiographical notes he produced in 1949, and he described it as a paradox he had hit upon at the age of 16 that contained the germ of special relativity. 10 years after Aarau, working as a patent examiner in Bern, he resolved it. And this is the moment I want to sit with, because it is easy to skate past. He did not resolve it by working out what the frozen wave would actually look like. He did not find a clever adjustment that made the picture consistent. He resolved it by discovering that the question could not be asked. There is no state of motion in which you are keeping pace with a beam of light. Not because the engineering is hard, not because you would need infinite fuel, but because the situation is not one the structure of the universe contains. The scenario is not difficult, it is absent. There is a specific dignity in a question good enough to be worth destroying. Most bad questions are just noise. This one was precisely wrong in the direction that mattered. And being precisely wrong about the right thing is worth more than being vaguely right about everything. A theory that reshaped physics, that gave us mass and energy as the same quantity, that underwrote the entire 20th century, began as a teenager's impossible daydream about riding a sunbeam, and it began by that daydream turning out to be impossible in a very particular way. But notice what happened afterward. The popular version of the story kept the daydream and threw away the resolution. It kept the rider on the beam and simply reported that his watch had stopped. That is exactly the piece Einstein removed. So when somebody says that light experiences no time, ask yourself what the sentence is doing grammatically. It has a subject, light, and it has a verb of experience, experiences, and a verb of experience needs someone to do the experiencing. The whole sentence is built around a point of view, and the entire content of the physics is that this particular point of view does not exist. This might sound like the kind of complaint a pedant makes at a dinner party, and I want to head that off, because it is not. If the correction stopped at, actually, the phrasing is imprecise, it would not be worth 2 hours of your evening. The correction is worth it, because when you remove the passenger, something has to take its place, and what takes its place is one of the strangest and least discussed facts about light. Light is not blank. Light is not a featureless nothing that simply crosses the universe without any internal state whatsoever. Something does accumulate along that journey. Something is counted precisely, and we can measure the count to a fraction of one, and it is the basis of some of the most sensitive instruments human beings have ever built. It is just not time. So we are going to build to that carefully, because it does not make sense until the geometry underneath it makes sense. And the geometry does not make sense until you know why light has one speed for everyone in the first place. And that story does not start with Einstein at all. It starts 300 years earlier, with a Danish astronomer in Paris, staring at a moon of Jupiter that would not keep to its schedule. Part 3. The first time a clock ran late. For most of recorded history, the speed of light was infinite, and that was a perfectly reasonable position to hold. Nothing in ordinary life betrays a delay. You flick a switch, and the room is lit. You open your eyes, and the world is there. Aristotle argued that light was not a movement at all, but a state, a condition of presence in a transparent medium, like the transparency itself, and therefore had no speed to have. Empedocles had suggested earlier that light must take time to get from one place to another, and Aristotle specifically rejected the idea as contrary to observation, which, given the observations available to him, it was. The first person to argue the other way, with real force, was Ibn al-Haytham, working in Cairo in the early 1100s, whose Book of Optics made two claims that took European natural philosophy another 500 years to accept. The first was that vision works by light entering the eye rather than by some emanation streaming out of it, which had been the Greek picture, and which fails for the simple reason that you cannot see in the dark. The second was that light does travel, and at a great but finite speed. He could not measure it. He was right anyway. Galileo tried to measure it, in the early 1600s, with the only technology available: 2 men, 2 shuttered lanterns, and 2 hilltops. One uncovers his lantern, the other uncovers his the moment he sees the first, and you measure the delay. Galileo reported that if the speed were not infinite, it was at any rate extraordinarily rapid, which is a graceful way of saying that his assistant's reflexes were the only thing he had succeeded in measuring. The answer, when it came, arrived from the sky, and it arrived sideways. Nobody set out to measure the speed of light. Somebody set out to fix a clock. In the 1670s, the Paris Observatory was working on the great practical problem of the age, which was longitude. Knowing your latitude at sea is easy. Measure the height of the noon sun or the pole star. Knowing your longitude requires knowing the time somewhere else, and no clock of that era could survive months at sea and remain accurate. So astronomers proposed a clock nobody had to build. Jupiter has moons, and those moons pass into Jupiter's shadow on a regular schedule visible from anywhere on the night side of the Earth. Io, the innermost of the large ones, goes around Jupiter in about 42.5 hours, which is a fast, frequent, convenient tick. Publish tables of when Io's eclipses will happen. Hand them to every ship's navigator, and you have a universal clock hanging in the sky. The trouble was that the clock did not keep time, and the man who worked out why was a young Dane named Ole Rømer. Picture the Paris Observatory in the autumn of 1676. The building is new, barely a decade old, and cold. The tables on the desk say that Io will emerge from Jupiter's shadow at a particular minute. Rømer has spent months tracking the discrepancies in those tables, and he has noticed a pattern that nobody has been able to explain. The eclipses run steadily early during the part of the year when the Earth is moving toward Jupiter, and steadily late during the part when the Earth is moving away, with a total swing across the year of about 22 minutes. In August, he does something that in 1676 is close to reckless. He announces, in advance, in front of colleagues, that the eclipse due on the 9th of November will happen about 10 minutes later than the published tables say. Now it is November, the telescope is trained, the predicted minute arrives, and Jupiter's shadow holds Io exactly where it is. 1 minute passes, then 5. The tables are wrong, publicly, and everyone in the room knows whose prediction is riding on it. And then, 10 minutes late, precisely as the young Dane said it would, the small point of light slides back into view. What Rømer had understood is the thing this entire evening rests on. The eclipse was not late. Io was exactly on time. The news of it was late, because the news had to travel, and when the Earth is on the far side of its orbit, that news has an extra 300 million kilometers to cross. A delay had turned into a distance. Time and space had, for the first time in history, been converted into one another by an experiment. Rømer never published a clean numerical value himself, and the figure that follows from his reasoning comes out around 220,000 kilometers per second. That is low by about a quarter, and almost the entire error comes from the fact that nobody in 1676 knew how big the Earth's orbit actually was. The number was wrong. The conclusion was not. Christian Huygens took the result and folded it into his own work on light as a wave, publishing the first estimate expressed in terms of Earth diameters per second in 1690. Giovanni Cassini, Rømer's superior, had floated the finite speed idea himself and then spent years arguing against it, partly because the effect was harder to see cleanly in Jupiter's other moons. Confirmation arrived from a completely unrelated direction in 1728. James Bradley was hunting for stellar parallax, the tiny annual wobble in a star's position caused by the Earth's own motion around the Sun, which would prove the Earth moves. He found a wobble, but the wrong one, in the wrong direction, at the wrong time of year. Every star he looked at traced a small ellipse on the sky about 20.5 arcseconds across, and the timing of that ellipse tracked the Earth's velocity rather than its position. The explanation is something you have done yourself. When you walk through vertical rain, you tilt your umbrella forward, because relative to you, the rain is coming down at a slant. Bradley realized he had to tilt his telescope forward into the direction of the Earth's motion for exactly the same reason, and the size of the tilt gives you the ratio of the Earth's orbital speed to the speed of light directly. That ratio turns out to be about 1 part in 10,000. Run the arithmetic, and you get a speed near 301,000 kilometers per second, within 0.5% of the modern value, and dependent on nothing you have to know about Jupiter or the size of the solar system. As a bonus, Aberration was the first direct physical proof that the Earth actually moves, arriving nearly a century after Galileo's trial. The 19th century brought the measurement down to earth. In 1849, Hippolyte Fizeau sent a beam of light through the gaps in a toothed wheel, spinning at up to 25 revolutions a second, out to a mirror 8.5 kilometers away on Montmartre and back, and adjusted the speed until the returning light was blocked by the next tooth along. He got about 313,000 kilometers per second. Leon Fouquet replaced the wheel with a rotating mirror in 1862 and got about 298,000. Foucault also used the same apparatus in 1850 to show that light travels more slowly in water than in air, which was the observation that finally killed Newton's theory of light as a stream of particles, because that theory predicted the opposite. Albert Michelson spent most of a career on it, bouncing light between Mount Wilson and Mount San Antonio with a rotating octagonal mirror, and by the 1920s he was quoting numbers within a few tens of kilometers per second of the truth. And then, in 1983, the chain closed in a way nobody in Roma's century could have imagined. The meter was redefined in terms of light. The speed of light in vacuum is now exactly 299,792,458 meters per second, by definition, because a meter is defined as the distance light covers in a particular fraction of a second. We do not measure the speed of light anymore. We measure everything else against it, which raises the question that broke physics. If light has a speed, what is that speed relative to? Part 4. What was the speed relative to? A speed is always a speed with respect to something. That sounds like a technicality, and it is in fact the hinge the whole century turns on. Consider sound. Sound moves through air at about 340 meters per second at room temperature, and that number is a property of the air, not of whatever made the noise. If you run through still air at 10 meters per second, the sound coming toward you closes at 350, and the sound behind you falls back at 330. This is not exotic. It is how every wave in every medium behaves. Because a wave is not a thing traveling through a medium, it is the medium doing something, and the speed of the doing belongs to the medium. By the middle of the 1800s, the evidence that light was a wave had become overwhelming. Christian Huygens had argued for it in the 1650s from the behavior of light in lenses and mirrors, particularly refraction, where a beam bends as it crosses from one material into another. Robert Hooke reached similar conclusions in England and made an enemy of Isaac Newton in the process, a feud so durable that for centuries there was a rumour that Newton had disposed of the only portrait of Hooke on taking over the Royal Society. Newton insisted light was made of tiny particles, corpuscles, and his argument was actually a good one. Waves bend around corners, which is why you can hear a conversation from around a doorway without being able to see the people having it. Light does not visibly do that. Newton's authority was enormous, and his answer held the field for a century largely on the strength of his reputation. It fell in 1801 when Thomas Young sent light through a pair of narrow slits and got, on the screen behind, a pattern of bright and dark bands. There is no way to make bands like that out of little bullets going through one hole or the other. There is an obvious way to make them out of waves. Throw 2 stones into a still pond and watch the ripples cross, reinforcing where crest meets crest and cancelling where crest meets trough. Light interferes. Therefore light waves. So, waves in what? The medium was called the luminiferous ether, and its required properties were an embarrassment. To carry transverse oscillations at 300,000 kilometers per second, it needed a stiffness that in any ordinary material would exceed steel by an enormous margin. To leave the planets undisturbed in their orbits for billions of years, it had to be perfectly frictionless. It had to be massless, transparent, undetectable by any means other than the light it carried, and present in the emptiest vacuum anyone could produce. Physicists accepted this contradictory specification because the alternative seemed worse. A wave with nothing waving is not a modification of the idea of a wave. It is the absence of one. James Clerk Maxwell sharpened both the promise and the problem beyond recognition. Maxwell arrived at Cambridge in 1850 and was informed that attendance at the 6 o'clock morning chapel service was compulsory, to which he is supposed to have replied that he thought he could manage to stay up that late. Between 1861 and 1865, he took the scattered laws of electricity and magnetism, which experiments had already shown to be entangled, and welded them into a single system. Buried inside that system, he found a wave. Pinch the electric field somewhere, and it does not simply relax back to nothing. It generates a magnetic disturbance, which generates an electric disturbance, which generates a magnetic one, the two regenerating each other and moving away together. And the speed of that wave was not a free parameter. It was fixed entirely by two numbers you could measure on a laboratory bench: the permittivity and permeability of empty space. And when Maxwell put them in, he got a speed indistinguishable from the measured speed of light. He wrote, in effect, that it was hard to avoid the conclusion that light is an electromagnetic disturbance. His equations placed no limit on the wavelength, which meant there had to be electromagnetic waves the eye cannot see, both longer and shorter than visible light. Heinrich Hertz went looking and found the long ones at Karlsruhe in 1886 and 1887, generating and detecting what we now call radio. Asked what use they might be, Hertz is supposed to have said he supposed there was none. He died in 1894 at 36. Within a few years, a young man on his family's estate outside Bologna was using Hertz's useless waves to send messages across miles, then across counties, then across the Atlantic, and in 1909, Guglielmo Marconi collected a Nobel Prize for it. Maxwell saw none of this either. He died of abdominal cancer in 1879, aged 48. But Maxwell's equations carried an unexploded charge. They gave one speed for light, full stop, with nowhere to insert the motion of an observer. If that speed was relative to the ether, then somebody moving through the ether should measure something different, and Maxwell's equations should take a different form for them. The Earth orbits the Sun at about 30 kilometers per second, so we are moving through the ether at least that fast at some point in the year, and the effect should be detectable. In 1887, in a basement at what is now Case Western Reserve University in Cleveland, Albert Michelson and Edward Morley went looking for it. Their instrument split a beam of light in two, sent the halves down perpendicular arms, bounced them off mirrors, and recombined them so that any difference in travel time would show up as a shift in the interference fringes. The whole apparatus floated on a bath of mercury so it could be rotated smoothly, and the arms were folded by mirrors to an effective length of about 11 meters. They expected a fringe shift of about 4/10 of a fringe as the Earth swung through the ether wind. They measured nothing, not a small effect, not an ambiguous effect. Within their error, no shift at all, no more than about 1/100th of a fringe. It has been repeated ever since with better and better technology, and the modern versions, using rotating cryogenic optical resonators, constrain any direction dependence in the speed of light to below 1 part in 100 million billion. Two men proposed a rescue, George Fitzgerald in 1889 and Hendrik Lorentz in 1892, suggested that objects moving through the ether physically shrink along the direction of motion by exactly the amount required to cancel the effect. Mathematically this works. The transformations Lorentz wrote down are the same ones relativity uses, and they carry his name to this day. But look at what the proposal actually is. It is a mechanism whose only function is to hide something from every possible experiment, forever. It saves the ether by making the ether undetectable in principle. In 1905, a 26-year-old examiner at the patent office in Bern took the other road. He asked what the universe would have to be like if the experiment was simply telling the truth. Part 5. The price of one speed for everyone. Einstein's paper of June 1905 is called On the Electrodynamics of Moving Bodies, and it is a strange document to read now. It has no references and no bibliography. It does not mention the Michelson-Morley experiment. The word relativity does not appear in the title, and it begins from two assumptions so mild-sounding that a reader might skim past them. The first is that the laws of physics look the same in every frame of reference that is not accelerating. If you are in a windowless carriage moving smoothly at constant speed, no experiment you can perform inside it will tell you whether you are moving or stationary. Galileo had said essentially this in 1632, using a ship's cabin and some flies. The second assumption is where the ground opens. Light travels at the same speed in vacuum for every such observer, regardless of how the source is moving. Take a moment with that, because the intuitive violation is severe. If I stand still and shine a torch, the light leaves at 300,000 kilometers per second. If you fly past me at 200,000 kilometers per second in the same direction and measure the same beam, you should get 100,000. That is how everything else in your experience behaves. You do not get 100,000. You get 300,000. You get the same number I do, and so does everyone else, no matter what they are doing. Now hold that fixed and see what has to break. Speed is distance divided by time. If two of us in relative motion must both compute the same value for the speed of the same beam, and we are demonstrably not covering the same distance in the same interval, then we cannot both be using the same distances and the same times. The constancy of the speed of light is purchased by giving up the absoluteness of space and the absoluteness of duration. Those were not assumptions anybody had thought to question. They were the flaw. What replaces them is a specific exchange rate. Moving clocks run slow by a factor that physicists write as gamma. Moving lengths contract along the direction of motion by the same factor. And simultaneity itself becomes a matter of perspective. Two events that I judge to happen at the same moment, you, moving relative to me, will judge to happen one after the other, and a third observer, moving the other way, will put them in the opposite order. There is no universal now. There is only your now and mine, and they do not match. That is a very large claim to make on the strength of one null result in a Cleveland basement, and it would be reasonable to be skeptical if the last 120 years had not been an unbroken run of confirmations. Start with something falling on your head right now. Cosmic rays strike the upper atmosphere and produce muons, which are essentially heavy electrons, about 15 kilometers up. A muon at rest lives on average 2.197 microseconds before it decays. Even traveling at very nearly the speed of light, 2.197 microseconds gets you about 660 meters. Muons should be produced 15 kilometers up and die about 600 meters later, and essentially none of them should reach the ground. In 1941, Bruno Rossi and David Hall measured the muon flux at the top of Mount Washington, 1,917 meters up, and then again at sea level. Far more muons survived the trip than the simple arithmetic permits, and the surplus matched the relativistic prediction. From our point of view, the muon's internal clock is running slow, so it lasts longer. From the muon's point of view, if you like, the 15 kilometers of atmosphere is length contracted into something it can cross comfortably. Both descriptions give the same answer, which is the point. In 1977, physicists at CERN did it under control. They stored muons in a magnetic ring at a gamma factor of 29.3, which stretches that 2.197 microsecond lifetime out to about 64 microseconds, and measured the decay rate directly. Agreement with prediction at roughly the 1 part in 1,000 level. Along the way, the muons were enduring a transverse acceleration of order a billion times the gravity you are sitting in, which made no difference at all to the result, ruling out an entire family of objections. In October 1971, Joseph Hafele and Richard Keating did the experiment with commercial airliners. They booked passenger seats for 4 cesium beam clocks, flew them around the world, eastward and then westward, and compared them with clocks left at the United States Naval Observatory. The total budget was around $8,000, which may be the best value for money in the history of experimental physics. The predicted eastward shift was minus 40 nanoseconds, give or take 23. They observed minus 59, give or take 10. Westward, the prediction was plus 275, give or take 21. They observed plus 273, give or take 7. You rely on this every time your phone works out where you are. The satellites in the global positioning system are moving fast enough that their clocks lose about 7.2 microseconds a day to velocity, and they are high enough in Earth's gravity well that they gain about 45.9 microseconds a day from the weaker gravitational field, for a net gain of about 38 microseconds every day. 38 microseconds does not sound like much. Light travels about 11 kilometers in that time. If the correction were switched off, position fixes would drift by roughly 10 kilometers per day, and the system would be useless by lunchtime. And in 2010, a group at the National Institute of Standards and Technology, led by David Wineland, pushed the measurement down to human scale. Using aluminium-ion optical clocks, linked by 75 meters of optical fiber, they resolved time dilation for one clock moving at less than 10 meters per second, which is roughly the speed of a fast jog. In the same set of experiments, they measured the gravitational effect across a height difference of 33 centimeters. Raise a clock by about a foot and it runs measurably faster. Not in principle, measurably. The list keeps going, and some of the best entries were written by people trying to prove the whole thing wrong. In 1938, Herbert Ives and G.R. Stilwell set out to test the transverse Doppler shift, the frequency change relativity predicts for a moving source, even when it is moving sideways rather than toward or away from you. There is no classical effect of that kind at all. It exists purely because the moving source's clock is running slow. Ives was a lifelong skeptic of relativity who expected to find a discrepancy. He found the predicted shift instead, and spent the rest of his career arguing that it should be interpreted in Lorentz's ether language rather than Einstein's. Later versions of his experiment, using lithium ions in storage rings at Heidelberg, have confirmed the time dilation factor to a few parts in a billion. Length contraction has moved from prediction to engineering in the same period. At the relativistic heavy ion collider on Long Island, gold nuclei run at a gamma factor near 100, and the physicists modeling their collisions do not treat them as spheres, they treat them as flattened disks, because in the laboratory frame, that is what they are. At the Large Hadron Collider, lead nuclei reach gamma factors near 2,900. If you built the machines, assuming rigid, unchanging nuclei, the collision geometry would come out wrong, and the data would not make sense. There is one caveat worth carrying forward. In 1959, James Terrell and Roger Penrose independently showed that a fast-moving object would not actually look contracted in a photograph, because light from its far side has to leave earlier than light from its near side to arrive at the same instant, and once you account for that, the image comes out rotated rather than squashed. The contraction is real in the geometry and absent from the picture. The relationship between what is true and what is seen has been quietly complicated since 1905, and light is the reason. So the trend is not in dispute. and it has been checked across more than 16 orders of magnitude in speed, from a walking pace to a hair's breadth from the speed of light. Faster means slower clocks, always, by exactly the predicted amount, and that is precisely why the naive extrapolation is so seductive. Follow the numbers. At 10% of light speed, gamma is 1.005, at half, 1.155, at 90%, 2.294, at 99%, 7.089, at 99.9, 22.4, at 99.99, 70.7, at 6 nines, 707. Every 9 you add multiplies the effect again. The clock is slowing and slowing and slowing. It is so natural to say that at the speed of light it stops. It is so natural, and the trend supports it so completely, that almost nobody looks at what the arithmetic actually does at that final step. The arithmetic does not arrive at 0. It goes somewhere else entirely. Part 6. The minus sign. The move that makes all of this tractable did not come from Einstein. It came from his old mathematics teacher, a man who had once described the young Einstein as a lazy dog. On the 21st of September, 1908, at a scientific congress in Cologne, Hermann Minkowski opened an address with one of the most quoted sentences in the history of physics. He said that from that hour onward, space by itself and time by itself were doomed to fade away into mere shadows, and that only a union of the two would preserve an independent reality. What he had noticed is that Einstein's 1905 paper, which reads as a set of rules about clocks and rulers, is much simpler if you stop thinking of space and time as two separate stages and start thinking of them as one four-dimensional geometry. Einstein initially dismissed the reformulation as superfluous erudition. He changed his mind completely within a few years, because without Minkowski's geometry, general relativity would have been unreachable. Minkowski himself did not live to see any of it. He died of a ruptured appendix in January 1909, at 44, 4 months after the address. Here is what he gave us, and it is worth going slowly because everything from here rests on it. In ordinary space, if you and I set up different coordinate systems, rotated relative to each other, we will disagree about the coordinates of 2 points. Your x and y will not be my x and y, but we will agree completely about the distance between the points, because distance is computed by squaring the differences and adding them, and that particular combination does not care how you have oriented your axes. Distance is the invariant. It is the thing that survives translation between viewpoints. Minkowski asked what the equivalent invariant is when you include time, and he found it, and it looks almost exactly like the ordinary distance formula, with one difference. You square the time separation, you square the space separation, and then instead of adding them, you subtract one from the other. That is the whole of it. One minus sign, sitting where every intuition you have says there should be a plus. That single minus sign is where relativity lives. It is the reason moving clocks run slow, the reason nothing overtakes light, the reason simultaneity comes apart, and the reason tonight's question has the answer it does. It is not an approximation or a modeling choice. It is the shape of the world. The quantity it produces is called the interval, and it is the separation between two events in space-time, and every observer in the universe computes the same value for it, no matter how they are moving. That is what makes it worth having. But because of the minus sign, the interval is not always positive, and this is where it stops resembling ordinary distance and starts telling you something about causality. There are 3 cases. If 2 events are separated by more time than space, the interval is what physicists call time-like. Concretely, that means something moving slower than light could be present at both events. You could be at the first and then be at the second. You could carry a clock from one to the other. And here is the beautiful part. The interval, in that case, is exactly the amount of time that clock would measure. Not the time anybody else assigns to the journey. The time actually elapsed on the thing that made the trip. That quantity has a name. It is called proper time, and it is as close as physics comes to an answer to what a traveler experiences. If two events are separated by more space than time, the interval is space-like. Nothing can be present at both, because you would have to outrun light to get from one to the other. There is no ordering that all observers agree on, and no clock can connect them. The interval in that case measures a proper distance instead, a length rather than a duration. And then there is the third case, and it is not a smooth blend of the other two. If two events are separated by exactly as much space as time, so that the subtraction gives you precisely 0, the interval is null. That is not a small interval. It is exactly, identically 0. And the condition for it, separated by as much space as time, is another way of saying that a beam of light emitted at the first event arrives at the second. Draw all the null directions from a single event, and you get a cone opening into the future and another into the past. This is the light cone, and it is not a diagram convention. It is a real structure sitting at every point of space-time. Everything you could ever affect lies inside your future cone. Everything that could ever have affected you lies inside your past cone. Everything else, the entire region outside, is causally sealed off from you forever, no matter how long you wait or how fast you travel. Your life is lived inside a cone, and the cone's surface is made of light. It is worth saying that the minus sign has been dodged more than once in the history of this subject, and every dodge has been abandoned. Henri Poincaré, writing in 1905 and 1906, produced a four-dimensional formulation of his own by making the time coordinate an imaginary number, which has the effect of burying the minus sign inside the arithmetic so that everything looks like an ordinary rotation again. It works, and modern treatments have quietly dropped it, precisely because the disguise hides the one thing you most need to see, that time is not a fourth direction like the other three, and that the difference between a route through space-time you could take and one you could not is exactly the difference the minus sign encodes. That structure is also not confined to flat, empty space. In general relativity, gravity tilts light cones. Near a very heavy object, they lean inward, and at the horizon of a black hole, they have tipped so far that every direction inside the cone, every future you could possibly have, points further in. A black hole horizon is not a wall or a surface made of anything. It is the place where the light cones have finished tipping, which is another way of saying it is a surface made of light held permanently in one position, going nowhere. Now hold that picture and look at where the light lives, because this is the sentence tonight turns on. Every path inside the cone has a proper time attached to it. Take any two events you could travel between, pick any route, and there is a real, positive number of seconds that a clock following that route would rack up. Different routes give different numbers, which is the entire content of the twin paradox. Two roads between the same two towns can have different lengths, and there is nothing paradoxical about it once you see it as geometry. In fact, and this is the one place where space-time inverts your intuition entirely, in ordinary geometry, the straight line is the shortest route between 2 points, but in space-time, the unaccelerated world line is the longest. The twin who stays home ages the most. The one who turns around took the shortcut, but the surface of the cone has no such number, and I want to be very careful here, because this is exactly where the popular version and the actual physics part company. It is not that the number on the surface is very small. It is not that the clock runs slowly there and the seconds compress toward nothing. It is that the quantity does not exist on that surface. Proper time is defined by the interval, and the interval along a null path is 0, and a zero-length parameter cannot label the points along a path. Physicists do label points along light paths, because you need to be able to say which part of the path you are talking about, and they use something called an affine parameter to do it. But that parameter is not time. It does not correspond to anything any clock would read. And crucially, you can rescale it however you like, without changing a single physical prediction, which is the giveaway. It is a mile marker. It tells you where you are on the road. It does not tick. So we can now say something quite precise, and it is worth stating, in a form you can carry. A clock is a thing you carry. That is what proper time is. It is not a rate at which the universe advances, and it is not a river everything is swept along by. It is a length, accumulated along the particular route you personally took through space-time, and it belongs to you and to nothing else. 2 different routes, 2 different lengths. That is why your clock and mine disagree after a journey, and that is why the disagreement is not an illusion or a trick of measurement. You went a different way. Which raises the question that the whole rest of the evening exists to answer. What happens to a thing whose route has no length at all? Part 7. Riding the beam. Honestly. Let us actually run the thought experiment. Not the summary of it, not the punchline, but the thing itself, step by step, and let us pay attention to what happens to the numbers as we go. You are aboard something that can accelerate for as long as you want. It does not matter how. We are not doing engineering tonight. Behind you is the Earth. Ahead of you is a star. And between you and it is a beam of light heading the same way you are, and your intention is to catch it. At 1% of the speed of light, you notice essentially nothing. 3,000 kilometers per second, and the clock on the wall is running slow relative to home by 5 parts in 100,000. The sky looks the way it always did. At half the speed of light, the changes are unmistakable. Your clock is running at about 87% of the rate of the one you left behind, and the sky has begun to move. Stars that were off to your sides have slid forward, crowding toward the direction you are traveling, and the ones ahead have shifted toward the blue. This is aberration, the same effect Bradley found in 1728, and it is the same reason you tilt an umbrella forward in the rain. At half light speed, it is dramatic rather than subtle. At 90%, your clock runs at about 44% of homes. The forward crowding has become severe. A hemisphere of sky is compressing into a patch ahead of you, brightening as it goes, while behind you the stars redden and thin out. At 99%, the factor is about 7. At 99.9, it is 22. The star field ahead is now a fierce, bright disk, blue shifted past visible light into ultraviolet and beyond, and the space behind you is going dark, not because the stars have gone, but because their light has been stretched out of your ability to see it. And this is the moment to notice the thing that everybody misses, because it feels like progress. Every increment of speed you add makes the effects more extreme, and it feels like you are getting closer. You are burning enormous energy for each new decimal place, and each new decimal place buys you a bigger factor than the last. 99.99 gives you 70. 99.9999 gives you 700. 6 nines gives you 7,000. 8 nines gives you 70,000. Now ask the question that undoes it. How many nines do you need? There is no answer, and not because the answer is a large number. There is no last 9. The sequence does not converge on anything. If it converged, you could name the value it converged to, and that value would be what the photon's clock reads. But a sequence that grows without bound does not have a limit that is a number. It has no limit. Which means the thing you were driving toward was never a destination. Look at what is happening to the space around you at the same time. Distances along your direction of travel are contracting. At gamma 70, the trip to a star 70 light-years away is, in your reckoning, 1 light-year long. At gamma 7000, It is a few light days. At gamma 70,000, a few hours. Push further, and the entire path ahead of you compresses toward nothing, and the sky ahead compresses toward a single point, and the sky behind compresses toward a single point, and the space between those 2 points is being squeezed out of existence. Take the limit and see what you are left with. The wavelength of the light you were chasing goes to 0 if you look forward and to infinity if you look back, which means the light you set out to describe no longer has any definite color at all. The angular position of everything in the universe collapses to one of 2 points, and every location along your line of travel has been contracted into the same coordinate, which means the star ahead and the Earth behind, and every point between them now all share a single address. You cannot tell them apart. You cannot say which is nearer. You cannot say anything about where anything is. That is not a strange map of the universe. That is not a distorted, hard to read, but technically usable description of what a photon would see. It is not a description at all. Every question you might ask of it returns either 0 or infinity or the same answer for everything. And a coordinate system that gives every event the same coordinate is not a coordinate system. It is a collapse. Before we go on, it is worth saying that the forward crowding is not a thought experiment flourish. Astronomers watch it happen. When a supermassive black hole at the center of a galaxy launches a jet of material toward us at something like 99% of the speed of light, the light that material emits gets swept forward into a narrow cone by exactly the effect we just described, and the result is that the jet appears far brighter than it has any business being, sometimes by factors of thousands. Astronomers call it relativistic beaming, or the headlight effect, and it is why a blazar, which is simply an ordinary active galaxy that happens to be pointing a jet at Earth, can outshine everything else in its sky. The aberration you would experience aboard the ship is a real, catalogued, measured feature of the universe. It is just usually happening to somebody else's light. There is a mirror image of this failure on the other side, and it is worth a sentence because it brackets the problem neatly. Suppose there were a particle that always moved faster than light, of the sort physicists sometimes call a tachyon. You could not construct a rest frame for that either, and for the same structural reason running the other way, you cannot slow such a thing down to a standstill any more than you can speed an ordinary particle up to light speed. The two impossibilities sit on either side of the light cone, and the null surface between them is not a midpoint, it is a boundary that belongs to neither side. Mathematicians have a word for a limit that behaves like this. They call it degenerate. And the everyday version of it is something you learned without noticing. In a maths class you have probably forgotten. Think about the slope of a line. A gentle line has a small slope. A steeper line has a larger one. Steeper still, larger still. And a vertical line has, what? Not a very large slope. Not infinity, if you are being careful. The slope of a vertical line is undefined, because the operation that produces slope involves dividing by the horizontal change, and the horizontal change is 0, and you cannot divide by 0. The vertical line has not got an extreme slope. It has stepped outside the category of things that have slopes. The photon frame breaks in exactly that way, at exactly that place, for exactly that reason. So when you take the picture everybody carries, the rider on the crest of the wave with the frozen watch, and you actually try to construct it rather than gesture at it, you do not find a rider whose watch has stopped. You find that there is no vantage point there to construct. The approach was never an approach. It was a direction along an axis that runs out. And notice, please, that nothing has gone wrong with the light. The beam you were chasing is perfectly well behaved. It has a definite energy, a definite momentum, a definite direction, and it will arrive at the star exactly on schedule. Everything about the photon is fine. The only thing that broke is the attempt to stand where it stands, which means the failure is not a fact about light. It is a fact about the question. Part 8. There is nobody on the beam. I want to make the argument properly now, rather than gesturing at it, because this is the load-bearing wall of the whole evening, and because popular accounts almost always skip it. Start with what a reference frame actually is, because the phrase gets used loosely. A reference frame is a way of labeling events with 4 numbers, 3 that say where and 1 that says when. That is all. It is a filing system for things that happen. Some observer sets it up, and then there has to be a rule for translating between their labels and somebody else's, so that 2 people who disagree about the numbers can still agree about the physics. In relativity, that translation rule is the Lorentz transformation, and the complete set of allowed transformations forms what mathematicians call a group. The word matters. A group has a specific closure property. If you apply one member and then another, the result is also a member. You can change your speed, and change it again, and you always land on another legitimate frame. There is no way to fall off the edge by accumulating boosts. There is a quantity that makes this beautifully clear, and it is called rapidity. Velocities do not add the way you expect in relativity. Half the speed of light plus half the speed of light does not give you the speed of light, it gives you 80% of it. Velocities saturate, but rapidity, which is a kind of angle that measures how far you have boosted, adds perfectly straightforwardly. Boost by 2 units of rapidity, then by 3 more, and you have boosted by 5. Rapidity 1 corresponds to 76% of light speed. Rapidity 2 is 96%. Rapidity 3 is 99.5. Rapidity 5 is 99.99. Rapidity 10 is about 99.9999996%. So the question becomes very simple. What rapidity corresponds to the speed of light? Infinity. And infinity is not a member of the group. There is no element of the Lorentz group, none, that takes an observer moving slower than light and maps them onto light itself. This is not a statement about energy budgets or engineering difficulty. If it were, you could imagine some advanced civilization solving it. It is a statement about what the set of transformations contains, and the answer is that the destination is not in the space of destinations. You are not being told the journey is long. You are being told there is no address. You can try to sneak up on it with a limit, and we did exactly that in the last part, and we watched it collapse. The wavelengths ran to 0 and infinity. The sky compressed to 2 points. The coordinates along the direction of travel all became the same coordinate. That is a degenerate limit, and a degenerate limit is not a viewpoint. It is the mathematical equivalent of a map on which every city has been printed on top of every other city. And there is a third version of the argument, the one Einstein himself walked into as a teenager, and it is the shortest. Suppose, for the sake of it, that you could ride alongside a light wave. What would you see? Maxwell's equations answer immediately. You would see an electromagnetic field that varies in space but not in time, peaks and troughs sitting still, and there is no such solution. Not no such solution that we have found, not a solution that would be hard to produce. Maxwell's equations do not contain one. An electromagnetic wave is the process of an electric change, making a magnetic change, making an electric change. Take away the change, and you have taken away the wave. What you are describing when you describe a frozen light wave is not light in an unusual state. It is a thing that has no representation in the theory that governs light. 3 separate lines of argument, from group theory, from limits, and from Maxwell, and all 3 arrive at the same place. There is no photon frame. So let us sit with what that costs, because it costs something, and I think it is worth grieving for about 30 seconds. The image is a good one, and it has probably been in your head in one form or another since you were young. A rider on the crest of the wave, the universe streaming past, a wristwatch frozen at a single moment for 13.8 billion years. It gives light a loneliness that is easy to feel something about. The eternal traveler who never ages, who crosses everything and is touched by none of it. And the physics is not telling you that the rider sees nothing. That would still be a story with a subject in it. The physics is telling you that there is no seat. The fastest thing in the universe, the thing that connects every part of the cosmos to every other part, the carrier of essentially every fact any of us has ever learned about anything beyond arm's reach, is the one thing in the universe with no account of its own journey. Not a blank account, not an account that reads 0. No account, because there is nobody keeping one. That is a stranger kind of loneliness than the one in the picture, and I think it is a truer one. It is worth being careful about what is and is not broken here, because it would be easy to come away thinking the photon is somehow an ill-defined object, and it is nothing of the sort. A photon has a perfectly well-behaved energy, a perfectly well-behaved momentum, and a direction through space-time that every observer can compute and agree on. All of those quantities transform beautifully between frames. There is exactly one thing about a photon that does not exist, and it is a frame in which the photon is at rest. Everything else is fine. The phrase, "from the photon's perspective," is a sentence with correct grammar and nothing to point at, in the same way that asking what lies north of the North Pole is a perfectly well-formed question with no answer, not because the answer is hidden, but because the direction runs out. And the photon is not a special case in this. Any massless particle travels on a null path and has no rest frame. The absence of one is not a quirk of light. It is what it means to be massless. Now, an objection, and it is the right objection, and if it has occurred to you already, then you are thinking about this correctly. If there is no photon frame, then what on earth is the status of the claim that the interval along a light path is 0? Is that not also a statement made from the photon's point of view? And if the point of view does not exist, does the claim not evaporate along with it? It does not, and the reason is the whole payoff of Minkowski's geometry. The interval is not a reading taken in some particular frame. It is the invariant. It is the one quantity that every observer, in every state of motion, computes the same value for. When we say the interval between the emission and the absorption of a photon is exactly 0, we are not reporting what a photon measured. We are reporting a property of the path itself, a fact about the shape of that route through space-time, and you can verify it from your armchair, and I can verify it moving at half-light speed, and a probe falling into a black hole can verify it, and we will all get 0. In fact, it is precisely the sort of statement that survives the absence of a photon frame. It may be the only sort. Every claim about light's journey that depends on a point of view has just been dissolved. What is left is the geometry, and the geometry says the two ends of a light path are separated by nothing at all. Which brings us to the distinction I want you to carry out of tonight, because everything from here hangs on it, and it is small enough to fit in one sentence. 0 is not the same as none. A clock that reads 0 is a clock. It exists, it has a face, and the face says 0. That is a measurement. That is a thing that happened. Whereas no clock at all is not a measurement of anything. It is a different category of situation entirely, and the mistake in the popular sentence is not that it gets the number wrong, but that it supplies a number where the physics supplies a category change. So we have taken something away. We took away the rider, and we took away the frozen watch, and what we have left, so far, is a path through space-time with two ends and apparently nothing in between, which would be a bleak place to leave it, and it is not where we are leaving it, because something does accumulate along a light path. Something is counted with a precision that beggars every other measurement human beings make, and the count is real, and it is the reason we can detect two black holes colliding a billion light-years away. It is simply not a count of seconds. Part 9. What light has been counting. Light keeps a ledger. It is exquisitely precise. It has been running the entire time, and almost nobody mentions it, because everyone is too busy talking about the clock light does not have. An electromagnetic wave oscillates. The electric field at a given point rises to a peak, falls through zero, drops to a trough, and comes back, over and over, and the position within that cycle is called the phase. As the wave travels, the phase advances continuously, and between any 2 points along a beam, there is a definite number of accumulated cycles. Not an approximate number, a definite one. For visible light, that count runs at somewhere between 400 and 790 trillion cycles every second. Green light, near the middle of what your eye responds to, oscillates about 545 trillion times a second. So a beam of green light crossing a single meter completes something like 1.8 million cycles on the way. Cross a light year and you are into numbers with more than 20 digits in front of the decimal point. Now, that would be a curiosity if the count were merely theoretical. It is not theoretical. We can measure it, and measuring it turns out to be the single most sensitive thing human beings know how to do. Here is the trick, and it is over 200 years old. Take a beam of light and split it in two. Send the halves along different routes. Bring them back together. If the two routes happen to differ in length by a whole number of wavelengths, the two halves arrive back in step, crest lining up with crest, and they reinforce. You get brightness. If the routes differ by half a wavelength, they arrive exactly out of step, crest lining up with trough, and they cancel. You get darkness. The pattern of bright and dark you see when you recombine them is a direct, physical readout of the difference in the number of cycles the two halves accumulated. Thomas Young did this with two slits and a candle in 1801 and settled a century-long argument about the nature of light. Michelson and Morley did it in 1887 and found the ether missing, and in the early hours of the 14th of September 2015, two detectors in Louisiana and Washington state did it with laser beams down 4-kilometer vacuum tubes and caught two black holes merging 1.3 billion light-years away. Think about what that measurement required. The gravitational wave passing through the Earth stretched one arm and squeezed the other by a fraction of about 1 part in 1,000 billion. Over 4 kilometers, that is a length change of roughly 1,000th of the width of a proton. And the instrument saw it, because the light in those arms had been keeping count, and the count changed. Sit with that count for a moment, because it is the part of light's journey that actually exists. Somewhere in a star 25,000 light-years away, on the far side of the galactic center, an electron drops between two states in an atom, and a wave begins. Crest, trough, crest, trough. 500 trillion times every second, by the reckoning of that star. It crosses the thinned-out gas between the spiral arms, and the count continues. It passes through a molecular cloud that will one day collapse into stars nobody alive will see, and the count continues. 25,000 years of our time go by, and there is no moment in any of it when the counting pauses, because the counting is not something the light does over time. It is what the light is. By the time that wave reaches the outer atmosphere of your planet, the tally stands at a number with more than 20 digits in it. And here is the part that should stop you. That number is recoverable. Split the beam tonight with a good enough instrument. Send the halves down two different paths. Bring them back together, and the pattern of light and dark will tell you the count to within a fraction of a single cycle. A ledger 25,000 years long, readable in an afternoon, with not 1 second recorded anywhere in it. So light is not featureless. Light has been recording something the entire way. in a form we can read out to a fraction of one cycle, and the fact that this is not the first thing anybody says about a photon's journey is a small tragedy of science communication. But there is a trap here, and I want to walk straight into it, and then out again. The obvious thought is that frequency must therefore be the photon's clock. It oscillates at a rate is a clock, and the photon has time after all. It does not work, and the reason it does not work is worth more than the answer. A clock, to be a clock, has to give the same reading regardless of who reads it. That is the whole job. If two people look at your wristwatch and see different numbers, you do not have a wristwatch, you have an argument. Proper time has this property. Everyone in the universe agrees about how much time elapsed on your clock between two events on your world line. Frequency does not have this property at all. Frequency is one of the least agreed upon quantities in physics. Move toward a source and you measure a higher frequency. Move away and you measure a lower one. Move fast enough and you can shift a given photon from radio to gamma rays or from gamma rays to radio, and there is no fact of the matter about which one it really is. Two observers handed the same photon can disagree about its frequency by a factor of 1,000 or 1,000,000, and both are correct. So if frequency were the photon's clock, it would be a clock whose reading changes depending on who happens to walk past it. That is not a clock. What frequency actually measures is not the photon's own history at all. It measures a relationship, the relationship between the photon and whoever is doing the observing. The photon's own contribution to that relationship is only a direction through space-time, a null direction, and a null direction has no scale attached to it. It tells you which way, it does not tell you how much. And the total accumulated phase, interestingly, is invariant. Everyone agrees on how many whole cycles fit between the emission event and the absorption event, which is exactly why interference fringes look the same to every observer. So light does have an invariant ledger. It simply has no seconds in it. There is one specific case where these two facts collide head-on and neither of them blinks. Come back to the photon from the beginning of tonight, released at recombination when the universe was 380,000 years old. When it left, the universe was at about 3,000 Kelvin, and the light being released was the color of a dim orange star. Today, that same light arrives as microwaves. Its wavelength has been stretched by a factor of about 1100, which means the energy of each photon has been cut by the same factor. It has lost more than 99.9% of the energy it left with. That is not a metaphor. We measure it directly. The cosmic microwave background sits at 2.72548 Kelvin, and there are about 411 of those photons in every cubic centimeter of the room you are sitting in. So hold both facts at once, because this is the shape of the whole answer. Along its own path, that photon is unchanged. The interval between its emission and its absorption is exactly zero, and it was zero at the start, and it is zero now, and nothing that happened in between altered it, because there was no in-between for anything to happen in. And in our accounting, that same photon has been drained. The expansion of space stretched its wavelength continuously for nearly 14 billion years and took almost all of its energy away. Where did the energy go? Nowhere. It is not conserved on cosmic scales, and it does not have to be. The conservation of energy follows from the fact that the laws of physics do not change from one moment to the next, and in an expanding universe, that particular symmetry is broken. The energy is simply gone. Both statements are true. They are not in tension, and the reason they are not in tension is the most useful thing you can take from tonight. Some facts about light belong to the geometry of its path. Those facts are invariant, and the zero interval is one of them. Other facts about light belong to the relationship between the thing that emitted it and the thing that absorbed it. Frequency is one of those, and so is energy, and so is color, and so is the entire history of that photon's reddening. There is no third category. There is no private, internal, experiential ledger sitting between the two. No diary the photon kept for itself. And looking for one is exactly the mistake the popular sentence invites you to make. Part 10. The Thing That Was Never a Thing. We have been telling a story all evening about a single photon crossing the universe. And it is a good story. And I now have to tell you how much of it survives contact with the theory that actually governs light. Less than you would like. Start with the question of what a photon is, which took physics about 25 years and a great deal of arguing to settle. Newton said particles. Huygens and Young and Maxwell said waves, and by 1900, the wave picture was so successful that the subject looked closed. Then it opened again in the most inconvenient way possible. Shine light on certain metals and electrons come flying off. That is the photoelectric effect, and by every expectation of the wave picture, it should behave in a particular way. Dim light should take longer to build up enough energy to knock an electron loose, and brighter light of any color should eventually do the job. Neither is what happens. Below a certain frequency, no electrons come off at all, no matter how bright you make the light or how long you wait. Above that frequency, they come off instantly, and their energy depends on the color, not the brightness. Turn the brightness up, and you do not get more energetic electrons, you get more of them. Einstein explained it in 1905, in the same burst of work that produced special relativity, by proposing that light delivers its energy in indivisible packets whose size is set by frequency. Red packets are small, blue packets are bigger, and if the packet is too small to free an electron, then no quantity of small packets will do it. Robert Millikan spent the better part of a decade trying to disprove this, and published a confirmation in 1916 instead. When Einstein received the Nobel Prize in 1921, the citation named the photoelectric law specifically. It did not mention relativity at all. Arthur Compton closed the case in 1923 by firing X-rays at electrons and finding that the X-rays came away with less energy and a longer wavelength, shifted by exactly the amount you get if you treat the collision as two billiard balls exchanging momentum. Not a wave washing over an electron, an impact, and the name we use only arrived in 1926, when Gilbert Lewis coined the word photon in a letter to the journal Nature, 21 years after the thing itself had been proposed. By 1924, Louis de Broglie, a French aristocrat whose family had been producing statesmen and diplomats since the Revolution, had drawn the obvious and outrageous conclusion in his doctoral thesis: if light can behave as both, then so can everything else. Electrons should diffract. They do. He collected a Nobel Prize for it in 1929. The experiment has since been run on molecules of more than 2,000 atoms, which interfere with themselves exactly as light does. So what is a photon? The modern answer, from quantum field theory, is not a small object at all. In this picture, the fundamental things in the universe are fields, and they are everywhere, including in perfect vacuum. There is an electromagnetic field filling all of space. There is an electron field. There are fields for each flavor of quark, for the gluons, for the neutrinos, for the Higgs, roughly 24 of them in the Standard Model, and every particle you have ever heard of is a quantized ripple in one of them. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. That is the whole ontology. Paul Dirac laid the foundation in 1927 in a paper on the emission and absorption of radiation that founded quantum electrodynamics. Dirac was a famously silent and literal man. Niels Bohr called him the strangest man he had ever met, and the anecdotes about his refusal to say anything unnecessary have outlived most of his equations in popular memory. What matters here is what his quantization showed. Emission and absorption of light are not extra rules bolted onto the theory. They fall out of the field description automatically. A photon is simply what you get when you ask how much energy the electromagnetic field can gain or lose at a given frequency, and discover that the answer comes in indivisible units. There is a consequence of all this that people find hard to believe even when they know it is true, and it is worth a moment because it makes the particle side of light physical in a way nothing else does. Light pushes. It has no mass, and it pushes anyway, because Maxwell's equations say that anything carrying energy also carries momentum, and delivering momentum is what pushing is. The force is tiny at everyday scales. Full sunlight at Earth's distance exerts a pressure of about 9 micronewtons per square meter on a reflective surface, which is roughly the weight of a grain of sand spread over an area the size of a door. But it never stops, and it costs nothing. And in 2010, the Japanese spacecraft Icaros unfurled a sail 20 meters across and demonstrated that you can genuinely sail between planets on nothing but starlight. The Planetary Society's Light Sail 2 raised its own orbit the same way in 2019. I should correct one thing here, because the desk toy everybody associates with this does not actually demonstrate it. The Crookes radiometer, the little glass bulb with 4 vanes that spin in sunlight, black on one side and silver on the other, is not driven by radiation pressure. It is driven by residual gas moving across the temperature difference between the two faces, and it spins in the opposite direction to the one photon pressure would produce. Light does push. That toy is not the evidence. 2 consequences of the field picture bear directly on tonight. The first is that photon number is not conserved. You cannot make or destroy an electron without balancing the books somewhere, because charge has to be conserved. Photons carry no charge, and there is no conservation law protecting their number. They are created and destroyed constantly, in unlimited quantities, in every atom in this room. One can become 2, many can become few. There is nothing about a photon that has to persist. The second is that identity gets slippery in a way that quietly dissolves our story. When light passes through glass, it is usually said to slow down, and something certainly takes longer to cross the glass than it would to cross the same thickness of vacuum. But what happens is that the electromagnetic field drives the electrons in the material. Those electrons radiate in turn, and the combined field, original plus re-radiated, propagates more slowly than light in empty space. Ask whether the photon that leaves the glass is the same photon that entered, and the field description does not so much answer as decline. There is a field. There is an excitation moving through a region where the field's behavior has been modified. The word same is doing work the physics does not support. And this matters, because the emotional weight of the popular story comes almost entirely from the idea of a persistent individual. A single small thing, enduring, unchanged, alone, for 13.8 billion years. That is what makes it moving. And field theory does not supply a persistent individual. It supplies a disturbance with 2 ends, an interaction where it began, an interaction where it stopped, and nothing in between that has any claim to being a thing with a biography. Which is, if you have been keeping track, exactly what the geometry told us in part 6, arriving now from a completely different direction. Relativity said the interval between the 2 ends is 0. Quantum field theory says there is no traveler between the 2 ends to have an interval. 2 theories that famously do not get along, agreeing precisely about this. That is usually a sign you are looking at something real. Part 11. When did the photon decide? I need to flag something before we start this part, and I want to be straightforward about it. Everything up to now has been settled physics, the kind that appears in textbooks and that no working physicist disputes. What follows is not. It is an interpretation, it is a minority position, and it may well be wrong. I am including it because it is the one serious attempt anyone has made to say something about the middle of a photon's journey, and because of where that attempt ends up. The story starts with an infinity that would not go away. In the 1940s, Richard Feynman was a graduate student working under John Archibald Wheeler at Princeton, and the problem in front of him was the self-energy of the electron. Here is the difficulty. An electron has an electric charge, and that charge produces an electric field around it. But the electron is sitting inside that field, so the electron feels its own field, and there is energy in that interaction. And when you calculate how much energy, the answer comes out infinite. Not large, infinite. The theory was producing nonsense for the simplest object it described. Feynman's response was to question the premise. He described it years later in his Nobel lecture in 1965, and the phrasing is characteristically blunt. He suggested to himself that electrons cannot act on themselves. They can only act on other electrons. Get rid of the field as a thing that exists on its own, and there is no self-energy to be infinite, because there is nothing for the electron to sit inside. It is worth knowing who was making this suggestion, because the confidence required to throw away Maxwell's field as a graduate student is not ordinary. In 1942, Robert Oppenheimer wrote a letter recommending Feynman for a position at Berkeley, in which he called him by all odds the most brilliant young physicist there, and said everyone knew it. He quoted two colleagues. Hans Bethe said he would rather lose any two other men than Feynman from the work then underway. Eugene Wigner said, more memorably, that Feynman was a second Dirac, only this time human. Feynman would spend the rest of his life generating anecdotes about himself at a rate that eventually irritated some of his colleagues, and Murray Gell-Mann said as much in public. He also produced the diagrams that every particle physicist still draws, and the path integral formulation of quantum mechanics, both of which grew out of this same period of trying to get rid of an infinity. But if you throw away the field, you have to explain radiation somehow, and that is where it gets strange. Maxwell's equations have two families of solutions, and this is a mathematical fact, not a speculation. One family, called the retarded solutions, describes a wave leaving a source and arriving somewhere later. That is what we observe, so that is what everyone uses. The other family, called the advanced solutions, describes a wave converging on a source from the future, arriving before it was sent. The equations permit both, with exactly equal enthusiasm. We discard the advanced ones because they seem absurd, not because the mathematics objects. Wheeler and Feynman kept both. In their absorber theory, published in 1945, and again in 1949, an emitter sends out a half-strength wave forward in time, and a prospective absorber, somewhere in the future, sends back a half-strength wave backward in time, and the two interfere in a very specific way. Between emitter and absorber, they add up to exactly the ordinary radiation we see. Everywhere else, they cancel out completely. Nothing leaks. And the reason radiation goes forward in time, rather than backward, in this picture, is not written into the equations at all. It comes from the fact that the universe is full of absorbers in the future, and comparatively empty of them in the past. John Cramer developed a quantum version of this in 1986, which he called the transactional interpretation. In his language, an emitter sends out an offer, an absorber sends back a confirmation, and the handshake between them is what fixes the transaction. The photon is not a thing that leaves one place hoping to find another. The photon is the completed agreement between the two. Now go outside and look at a star. Take a specific one, not the sky in general, one star. Somewhere in the outer atmosphere of that star, an electron in an atom drops from one energy state to a lower one. And somewhere in the back of your eye, in a molecule of retinal, folded into a protein, in one cell of your retina, an electron rises. Between those two events lie a few hundred years. or a few thousand, by any reckoning you or I would use. Along the path connecting them, there is nothing. Zero interval. The emission and the absorption are, in the geometry, adjacent. The transactional picture says something that follows naturally from that, and still lands strangely. Those two electrons agreed. Not in sequence, with one deciding and the other finding out later, but as a single joined event with two ends, one of which happens to be in the star's past, and the other in your present. You are not watching that star. You are one end of an interaction that has the star at its other end. And for our photon from the beginning of tonight, the one released when the first atoms formed, the handshake spans nearly the entire age of the universe. Now let me put the guardrails back up, because I said I would. This is an interpretation. As far as anyone has been able to show, it makes no prediction that differs from ordinary quantum electrodynamics, which means no experiment currently distinguishes it. It has faced serious technical objections, particularly about what happens when the future absorber is contingent rather than certain, and proponents have modified it in response, and the argument continues. It is not required to make sense of anything else we have discussed tonight, and if you would rather set it down entirely, nothing in the rest of the evening breaks. But here is why I brought it up, and it is not for the strangeness. The mainstream formalism, the completely uncontroversial machinery that every particle physicist uses every day, already has this feature in a quieter form. When you calculate what happens when light passes between two charged particles in quantum electrodynamics, you do not compute the photon's journey and then compute its arrival. You compute an amplitude connecting the emission event to the absorption event as a single quantity, with the photon appearing inside the calculation as an internal line rather than as an object with a life of its own. The two ends are handled together because they are two ends of one thing. So the interpretation is contested, and the formalism is not, and they are pointing in the same direction. The most exotic reading available, and the most conservative one, both describe a light path as one joined event, rather than a passage undertaken by a traveller, which is by now a familiar result. Relativity removed the passenger, field theory removed the persistent object, and the one serious attempt to describe the middle of the journey concluded that the journey does not have a middle. 3 independent routes, and none of them finds anybody home. Part 12. Light in a Bent Universe. Everything we have built tonight was constructed in flat, empty space-time, and the universe is neither of those things. So it is worth checking whether curvature changes the answer, because if it did, everything above would be a beautiful idealization with no bearing on the actual sky. It does not change the answer, it changes almost everything else. In general relativity, light follows what are called null geodesics. Geodesic means the straightest available path through a curved geometry, the same way a great circle is the straightest path across the surface of the Earth. Null means the interval along it is still exactly 0. That is the key point, and it survives intact. Curvature bends the road, but the road is still a road of 0 length. Newton, of all people, guessed at the bending. In Optics, published in 1704, he asked whether bodies act upon light at a distance, and by their action bend its rays. He was thinking of light as a stream of particles, feeling a gravitational pull, which is the wrong mechanism, and he arrived at roughly half the correct answer for the wrong reason. Nobody checked for 215 years. The check came on the 29th of May 1919, during a total solar eclipse, with expeditions to Principe, off the coast of West Africa, and to Sobral in Brazil. The measurement was to see whether stars appearing near the darkened sun had shifted position, and the shift they were looking for was about 1 3/4 arcseconds, which is roughly the angle subtended by a coin at a distance of 2 kilometers. The Newtonian prediction was half that. The measurement came out on Einstein's side, and it made him, within weeks, the most famous scientist alive. That effect is now a working tool rather than a test. Galaxy clusters bend the light of everything behind them, acting as lenses, magnifying distant galaxies that would otherwise be far too faint to see, and smearing them into arcs and rings. The distortion pattern lets astronomers map where the mass is, including the mass they cannot see, which is how a great deal of what we know about dark matter was learned. Every long-exposure image from the James Webb Space Telescope is full of these arcs. Curvature also delays light, and this is the effect that matters most for our question. Erwin Shapiro pointed out in 1964 that a radar signal sent past the Sun to Venus and back should take longer to return than a straight-line calculation predicts, because the path passes through curved spacetime. For a signal grazing the edge of the Sun, the extra delay is about 200 microseconds on the round trip. It was measured with planetary radar in the late 60s, and in 2002, the Cassini spacecraft nailed it down to about 2 parts in 100,000. But look carefully at what is being delayed. The arrival, as measured by a clock far from the mass. The interval along the light's own path is still exactly 0, and stays 0, all the way through. Curvature changes the route, and it changes how distant observers account for the trip. It does not hand light a clock. There is a companion effect worth naming, because it is the one people confuse with the delay. Light climbing out of a gravitational well loses energy as measured by an observer higher up, arriving redder than it left. Robert Pound and Glenn Rebka measured this in 1959 by sending gamma rays up a lift shaft in a building at Harvard, a height difference of 22.5 meters, and detecting a frequency shift of about 2 parts in 1,000 million. Again, a change in the accounting between two observers. Again, nothing at all done to the interval along the path. And it is not only light. In August 2017, 2 neutron stars merged 130 million light-years away. The gravitational waves arrived at detectors on Earth, and a burst of gamma rays arrived 1.7 seconds later. After 130 million years of travel, 1.7 seconds apart. That constrains the difference between the speed of gravity and the speed of light to about 1 part in 1,000 million. The null structure of spacetime is not a peculiarity of electromagnetism. It is the geometry, and gravity obeys it too. While we are being thorough, there have been attempts to give light a history of its own, and it is worth saying what happened to them. The most serious is the tired light hypothesis, proposed by Fritz Zwicky in 1929. Zwicky suggested that the reddening of distant galaxies is not due to expanding space, but to photons gradually losing energy to some interaction over enormous distances. If true, light really would accumulate wear along its journey. It fails 3 independent tests. It predicts that distant images should be blurred by whatever scattering process drains the energy, and they are not. It cannot reproduce the cosmic microwave background spectrum, which is the most perfect blackbody ever measured, with deviations below 50 parts per million. Scattering mechanisms distort blackbody curves, and this one is not distorted. And it makes no room for the observed stretching of distant supernova light curves, which unfold more slowly the further away they are, by exactly the factor expansion predicts. There is also a small research program exploring cosmologies in which the speed of light differed in the very early universe, associated with João Magejo and others. These are published, serious, and unconfirmed, and in any case, they do not touch the argument, which follows from the geometry whatever the local value happens to be. And there is a genuine open point that gets misused. It is true that nobody has ever measured the one-way speed of light. Every measurement ever made is a round trip, because measuring a one-way speed requires 2 synchronized clocks in different places, and synchronizing them requires already assuming something about how fast signals travel. This is a real conventionality, discussed carefully since Reichenbach in 1928. What it is not is a crack in relativity. No experiment has ever found any directional dependence, and every observable prediction of the theory is independent of which synchronization convention you adopt. So the picture holds in curved spacetime, holds against every alternative anyone has seriously proposed, and holds for gravity as well as for light. Which means it is time to go back to where we started, and look again at the oldest thing in the room. Part 13. The oldest light in the room. Let us step back and put the pieces together, because we have gathered a lot of them, and they belong in one stack before the last part. We began with a claim: light does not experience time. We found that the claim is a translation of a geometric fact, and that the translation smuggles in a passenger. We watched the passenger fail to exist, 3 separate ways. We found that what does exist along a light path is a count of cycles, invariant and measurable to a fraction of 1, containing no seconds. We found that the object we were imagining making the journey is not, in the deepest description we have, an object at all. And we found that curvature bends the road without giving the traveller a clock. Now come back to the photon we started with, because it is not an abstraction, and it is not somewhere else. It is here. Right now, in the room you are in, at a rate you cannot feel and could not stop, roughly 411 photons per cubic centimeter are passing through everything. Through the walls, through the floor, through the air in front of your face, through your clothes, through your skin, through the bone of your skull, and out the other side, without slowing down. They are microwaves, at a temperature of 2.72548 degrees, above absolute zero, and they are coming from every direction at once, with almost perfect evenness. They left when the universe was 380,000 years old. Sit with the arithmetic of that for a moment. When those photons were released, there were no stars, not young stars, not primitive stars, none. There were no galaxies, no planets, no carbon, no oxygen, no iron. The universe was hydrogen and helium at 3,000 degrees, cooling, and the only structure in it was a set of density ripples, so faint you would need instruments to find them. Everything that has ever happened after those photons were already in flight. And in the intervening 13.8 billion years, the overwhelming majority of them have interacted with nothing whatsoever. They have crossed the entire history of the universe untouched. Which means that for a great many of the photons passing through your body, in the next second, your body is the first thing that has ever happened to them. Not the first interesting thing, the first thing, since the beginning. If you have ever wanted a reason to feel implicated in the universe, rather than adjacent to it, that is the one I would offer. We found this light by accident, which is somehow appropriate. In 1964, Arno Penzias and Robert Wilson were working with a horn antenna at Bell Labs in Holmdel, New Jersey, trying to make radio astronomy measurements, and they had a hiss they could not get rid of. It came from every direction. It did not change with the time of day or the season, which ruled out anything terrestrial and anything solar. They checked the electronics, they cooled the receiver, they found a pair of pigeons nesting in the horn and evicted them, and cleaned out what Penzias diplomatically called a white dielectric material, and the hiss remained. It took a phone call to a group at Princeton who had been building an instrument to look for exactly this signal, for anyone to realize that the noise they could not remove was the oldest light in the universe. They won the Nobel Prize for it in 1978. Every television set built before digital broadcasting picked up a fraction of that same signal. If you are old enough to remember the static on an untuned channel, a small part of what you were watching was light released before the first star. That is the light in the room with you tonight. If you could see in microwaves, there would be no dark. There would be a faint, even, unvarying glow, filling the entire sky in every direction, with no gaps, no shadows, and no source you could point to, because the source is not in a direction. The source is in the past, and the past surrounds you. Now put the two facts side by side, the ones this whole evening has been building toward, and notice that they do not fight. By our accounting, those photons have had a rough journey. They left as visible light, the color of an ember, and they arrive as microwaves. Their wavelength has been stretched by a factor of about 1100 by the expansion of space, which means each one carries roughly 1/1100th of the energy it started with. More than 99.9% of it is gone. Not transferred, not stored, not hiding somewhere. Gone. Energy conservation is a consequence of the laws of physics staying the same from one moment to the next. And in a universe whose scale is changing, that particular guarantee does not apply. The universe took the energy, and there is no account it went into. That is a history. That is where. That is the closest thing to aging that can happen to light, and it is real and measured and dramatic. And along its own path, the interval between the moment that photon was released and the moment it is absorbed by an atom in your hand is exactly 0. It was 0 when it left. It is 0 now. Nothing that happened in between changed it, because the geometry does not have an in-between for anything to happen in. Both true, simultaneously. Not a paradox, not a trick of language, and not two ways of saying the same thing. One of them is about a root, and the other is about a relationship. And the reason they can both be true without contradiction is that they are answers to two different questions that sound like one. The resolution is the division of labor we found earlier, and it is worth stating one final time, plainly, because it is the actual answer underneath the answer. Some facts about light belong to the shape of its path through spacetime. Those are invariant, and every observer agrees on them, and the 0 interval is the chief one. Other facts about light belong to the relationship between the thing that emitted it and the thing that absorbed it. Color, energy, frequency, and the whole story of that 1100-fold reddening are all in this second category. They are not the photon's private business. They are the terms of a transaction between two ends. There is no third column in the ledger. There is no experiential category, no interior, no diary, no place where the photon kept its own account of the 14 billion years. And I think the reason this is so hard to accept, and the reason the popular sentence persists despite being wrong, is that we cannot help hearing no experience as a description of a very lonely experience. We hear it as an absence that somebody is suffering. It is not. The photon is not enduring an eternity compressed into an instant. There is no endurance. There is a path with two ends, a count of cycles along it, and two events that the geometry says are adjacent. The refrain we used at the start of tonight was that the photon sped on and noticed nothing. Through the dark ages, through the first stars, through the assembly of the galaxies. And I chose those words carefully, because they are how the story is always told, and because they are still, even now, slightly wrong in the same old way. It is not that the photon noticed nothing. We have one part left, and it is the part where I tell you what it is instead. Because there is a plain, sayable answer to the question in the title, it has been waiting since part 6, and it is smaller and stranger than anything we have said so far. Part 14. The answer, plainly. Here it is, without hedging. Light does not experience time, and the reason is not that its clock reads 0. The reason is that it never carried a clock. That is the whole of it. Everything tonight has been the work of making that sentence mean something, and now that the pieces are in place, it can be unpacked in a couple of minutes. A clock is a thing you carry. We established that in part 6, and it has been true every time we have come back to it. Proper time is not a rate at which the universe advances, and it is not a current that sweeps things along. It is a length. It is the amount of path you personally accumulated, getting from one event to another, measured along the particular route you took, and it belongs to you and to nothing else in the universe. Two people who take different routes between the same two events accumulate different lengths, and when they meet again, their watches disagree, and neither of them is wrong. They went different ways. Light takes a route of 0 length, not a short route, not a route so compressed that the accumulated time rounds down to nothing, a route on which the quantity does not accumulate at all, because the geometry that defines the quantity gives exactly 0 along every part of it. There is no odometer, because there is no distance for an odometer to register. There is no clock, because a clock is an odometer for a road that light is not on. And 0 is not the same as none. A clock that reads 0 is a clock, sitting there with a face, reporting a measurement. No clock at all is not a report. It is a different kind of situation. The error in the sentence everyone repeats is not that it gets the number wrong. It is that it supplies a number where the physics supplies a change of category, and once you have accepted a number, you have accepted a reader, and once you have accepted a reader, you have put somebody on the beam who cannot be there. That is the correction. And I said at the start that it was worth 2 hours because the true version is stranger than the popular one, so let me finish paying that off. The popular version leaves light blank, an eternal traveller who crosses everything and registers none of it, arriving as young as it departed, a kind of beautiful emptiness, and light is not blank. Light has been counting the entire way. Every beam that has ever crossed the universe has kept a perfect invariant tally of its own cycles. A number that everybody agrees on, a number so exactly kept that we can split a beam, send the halves 4 kilometers apart, bring them back together, and read out a discrepancy 1/10,000th the width of a proton. Light keeps better books than anything else we have ever built an instrument to read. There is simply not 1 second recorded anywhere in them. And there is a smaller consolation buried in that, which I have grown fond of. The reason we can read light's ledger at all is that we are the kind of thing that has a clock. The count only becomes information when it lands on something that accumulates duration, something with a world line of positive length, something that can hold 2 arrivals apart and compare them. A universe made only of light would have a great deal of counting going on in it, and nothing anywhere able to tell that any of it had happened, because there would be no interval between any 2 events for the counting to be spread across. Every detector, every eye, every instrument we have ever pointed at the sky works because it is slow. Our slowness is not a limitation on our access to the universe, it is the entire mechanism of it. So the honest picture is not an empty traveller. It is a thing that was never issued a watch, and which has been keeping meticulous records of something else the entire journey, and which we have spent a century describing as though the absence of the watch were the interesting part. Which brings me to the thing that has been sitting underneath all of this, and I will leave it open, because it is open. There are 2 ways to think about what time is. In the first, time flows. It is a current, a movement, something the universe does, and everything in the universe is carried along by it at some rate. That is how it feels from the inside, and it is very nearly impossible to stop thinking in those terms. And in that picture, light is a puzzle, because if time flows, then light must be in the current somewhere, moving at some rate, however small. In the second, time is not a flow, but an accumulation. It is not something that happens to you, it is something you gather by taking a particular route through a geometry, the way distance is something you gather by walking. In that picture, there is nothing puzzling about light at all. A route of 0 length accrues nothing, and that is not mysterious, that is arithmetic. People sometimes take the second picture further and conclude that if time is a geometry rather than a flow, then the whole of it must already be laid out, past and future together, with our sense of movement through it being a feature of us rather than of the universe. That is the view philosophers call eternalism. And it does sit comfortably with everything we have said. The zero interval does not compel it, though. And I want to be careful not to hand you a conclusion the physics has not paid for. The geometry is the same, whichever way you prefer to read what time fundamentally is. What the geometry does insist on is narrower and harder to argue with. That duration is a property of roots, and that some roots have none. Relativity supports the second picture completely, and has for 120 years. Every experiment we discussed tonight, the muons and the flying clocks and the satellites and the ion traps, is a measurement of accumulated path length. Not one of them measures a rate of flow, because there is nothing to measure it against. And the second picture is the one that makes the least sense to a creature like you, because you experience time as passage, as something moving, as a now that keeps arriving. The gap between the geometry that works and the intuition that does not is not going to close tonight, and may not close at all. But here is the piece I would like you to take to bed with you. Everything you know about anything more than arm's length away was delivered by light. Every color you have ever seen, every star, every photograph of a planet, every measurement of a distant galaxy, every scrap of evidence for the age and size and shape of the universe. It all arrived by the same mechanism, and that mechanism has no account of the delivery. The universe's entire information channel is made of carriers that cannot testify. The photon that began this story left when the first atoms formed and ended in a detector above the Earth, and I told you that it passed through the Dark Ages and the first stars and the assembly of the galaxies, and that it noticed nothing. That was the story as it is usually told, and I have been quietly correcting it all evening, so let me finish the correction now. It is not that the photon noticed nothing. There was never a photon there to do the noticing. There was an emission and an absorption, and between them, a path of zero length carrying a count of cycles with no seconds in it, and the 14 billion years belonged entirely to us. That is why light doesn't experience time the way you think. Not because its clock stopped, because there was never a clock, and never a wrist to wear one, and the whole time we have been asking what light went through. The honest answer has been that going through things is something only we do. The light is still arriving. It is arriving right now. 411 photons in every cubic centimeter, from a moment before there were stars, and by its own reckoning, it left an instant ago. Sleep well.